which is, again, this is more practical, more application type of topic. We're going to look at the transportation and the assignment problems. And this is material that is in part coming from your textbook, chapter 5. And this is, again, going back to formulation. You remember one of the first things we did in this class was to formulate several types of problems. But I also mentioned at that point that you can come up with some recipes. If you identify this problem looks like this, you can usually take the formulation, a general formulation, and apply it to that problem. One of those recipes, calling them recipes, is the transportation problem, because it's a very general format that you can apply to multiple problems, not only transportation, but other applications. So if you understand the problem, if you understand how it's formulated, again, you're going to have some supply, some demand, you can use that recipe and you can apply it to different applications. Transportation model is very important. It's very useful, especially in logistics. Companies such as Walmart, HEB, UPS, Dell, all those companies that are involved with shipping something, transportation problem is very useful because you want to be able to move your product as efficient as possible, paying the less money that you need to pay to increase your revenues. Okay, but the transportation problem will involve different things such as the time it takes to run truck from point A to point B, the cost of moving that truck, and so on. So in this class, this lecture, we're going to study the transportation and the assignment problems, and we're going to consider only a few items that affect the problem. We're not going to add a lot of detail. We're basically going to focus on the cost that takes to move one or a particular vehicle from one point to another point in the map. Okay, so transportation problem and the assignment problem. Okay, so again, I've been showing this slide a lot at the beginning of each lecture. So these are the course objectives, and we are basically at the last bullet: recognize, analyze, formulate, and solve industrial problems that can deal with linear programming. Two of those problems are the transportation and the assignment problem. Okay, so the learning objective is to discuss two special types of linear program: transportation and the assignment problem. And these are the recommended readings from your textbook. So 5.1 and 5.4. In the agenda, definition of the transportation problem, we're going to discuss what does it means to have a balanced transportation problem and the assignment model. Okay, so a general description: transportation problems deals with the problem of finding the best way to fulfill the demand of end demand points. So you have multiple clients, different points in the state, and you want to fulfill those demands. You have your warehouse located here in San Marcos. You want to find the best way to ship your product to your clients and spend the less money that you can spend. Okay, so you want to minimize your cost. You see the capacities of your end supply points. So usually, if you are a big company, you have multiple supply points. Let's say you are worldwide, so you will have supply in Europe, supply in North America, supply in South America. If you want to ship to different countries, you need to find out which supply point will cost you less to supply a specific client. Okay, so you have end demand points and supply points. Generally, a variable cost of shipping the product from one supply point to a demand point is taken into consideration. So there will be some costs involved. There will be transportation costs, maybe type of transportation that you're using, or maybe is the time it will take you to take the product to a particular location. So there will be some penalty if you don't deliver on time. So you need to take that into account as well. So there's multiple things. Again, we're going to focus only on the transportation cost, but those other details can be added to the model easily. So instead of discussing a transportation or vehicle type of problem, decided to start with a different type of problem to show you that even though it's a transportation problem, usually you think about vehicles, trucks, airplanes, and so on. You can also apply that same format or same transportation model to other applications such as the power generation. So usually when you have a generation plant and you want to supply your electricity to different points in the network. So residential consumers, you also have commercial industries, and you want to know which generation plant or power station should supply that particular point in the network. So the example refers to this company called Powerco Corporation, and has 3 electric power plants that supply the electric needs for 4 cities. The associated supply of each plant and demand of each city is given in table 1. So this is the table. You have 3 plants, and you have a supply for each plant. So plant 1 can supply 35 million kilowatts. So this is for plant 1. Plant 2 can supply 50, and plant 3 can supply 40. Okay, those are the capacities you have for each plant. Now, the associated supply of each plant and demand of each city is here again. So the demand for each city is listed on the bottom. So city 1 requires 45 million kilowatts, city 2, city 3, and city 4. So you have 3 plants producing this power, and you have 4 cities that depend on those plants for their supply. You also have some costs. The cost of sending 1 million kilowatts of electricity from a plant to a city depends on the distance the electricity must travel. So if you supply 1 million kilowatts to city number 1 from plant 1, this is your cost in million, and so on. So you have a cost from point A to point B. So plant 1 to city number 2 is 6 million, plant 1 to city 3, and so on. So this matrix is basically giving you the cost for moving that electricity from this plant to this city. Any questions? Do you understand what the problem is, what you're trying to do with this problem, right? You're supplying, and you want to satisfy the demand for your plant. Okay? So, the transportation problem is specified by the supply, the demand, and the shipping costs. The relevant data can be summarized in the transportation tableau, and the transportation tableau implicitly expresses the supply and the demand constraints and the shipping cost between each demand and supply point. So that tableau is what we saw on the previous slide. So you have the demand, you have the supply for each source, and you have the cost from one point to another. And this is the transportation tableau here. This is what I showed you on slide 8. Are you able to finish your notes? Okay. Okay, so now what we're going to do is we're going to formulate this problem. And you're going to help me formulate this problem. So let me see if I have a marker here. Okay, so anyone knows how can you define the decision variable for this problem? Any guess? So you're trying, yes. The plans are already stated, those are fixed. You know how many you have, you know how many clients you have. What is the question you're trying to answer? You have your plans, you have your customers. No? Yeah, the decision variable is xij, but I want you to tell me what xij is going to be. What's the meaning of xij? Correct. That's the question you want to answer. You want to know how much you're going to send from plant I to customer J. Okay, so xij is the amount of electricity produced at plant I and sent to city J. So if you have x14, that means that your decision variable is the amount of electricity produced at plant 1 and sent to city 4. So amount of electricity produced at plant 1 and sent to city 4. Okay, does that make sense? Okay, so every time that you're trying to define a decision variable, what you do is you ask yourself, what is the question you want to answer with this problem? In this case, we want to know how much you're going to send from a plant to a city. Okay, so the objective function, so to minimize the total cost of shipping from plants to city, so we have 3 plants, 4 cities, so we need to define our objective function based on those. So we know our decision variables. I believe you don't have this table in your slide, but it's the same table I showed previously. So I added here just to make it easier for you to see how to write the objective function. So what you're going to do is you're going to take each item in the tableau and you're going to state a decision variable for that item and make it part of the objective function. So for the first, you know that it's going to take, or it's going to cost you $8 to go from plant 1 to city 1. And then it's going to cost you $6 to go from plant 1 to city 2. It's going to cost you $10 to go from plant 1 to city 3. And it's going to cost you $9 to go from 1 to 4. Now you have to do the same for plant 2. So you have plus 9 to 1. You go from plant 2 to city number 1. Then plus 12 x to 2 and plus 13 x to 3 plus 7 x to 4. So we did this one, this one, this one, this one, this one. Then we have plus 14x31 plus 9x31 X32 plus 16X33 plus 5X34. So you want to minimize the cost of supplying your demand. You know the cost, so you want to minimize that cost. Okay, so the solution should give you the amount that plant A1 is going to supply to each city is going to be the one that is more cost effective. Questions about the objective function. So again, every time you see a problem that can be formulated as a transportation problem, this is how you're going to formulate the objective function. Okay, so you look at the cost, you know the cities, the supply, the demand, formulate your objective function. Now, we're going to have some supply constraints. So since each supply point has a limited production capacity, we need to provide a constraint to limit that production capacity. So we know that for plant 1, the capacity is 35, plant 2 is 50, and plant 3 is 40. So we're going to use that information to formulate the constraints for the supply. Anyone want to try to write one of the constraints for a bonus point? I can have two. If you want, try there and have someone else here. There's no markers. And I will add that point to the current exam. Exam number 2. So I mean, it's worth it if you want to try. And you cannot cheat because the constraints are in 16. Okay. Yeah.
So that's the plan.
So you're going to have a constraint for each plant, yeah, basically. So you know that that plant can only supply this amount. So you're going to be doing the first one, which is for plant 1. So at least you know that it has to be less than or equal to 35. Yes. You want to try it?
Well, I don't know. I want to make sure that I'm on the right track as to what I can give my team. So you're implementing the XIJ rule in the constraints as well?
Yes.
Okay, got that.
Yeah. Okay. So I can try to formulate for the second plant, but I don't have any extra markers. I don't know what happened. I used to have a lot of them here. You can write it in your paper and then, yeah.
I'll try that.
Demand, yeah. You'll wait for the next one.
Or just X2, X2.
I mean, you can help each other. That's okay. I'll come up with the right constraint. So remember, Xi is the plant, J is the customer. So if you're writing constraint for a plant, your I should stay the same.
So would this be for plant 2?
So, yeah, but you don't have to specify the cost because the costs are going to be
Okay.
So it will be this.
Okay.
Yes. Would this be for demand? Like demand is
Yes. For the demand instead of being 10 to make greater.
Oh, yeah.
Okay, good.
So, yeah, that's right.
Just double check. So you have 2, 3, 1, 1, 1, 2, 2, 2, 2. Yeah, yeah. So that's correct. So, so since all of you were helping, I'll give you a point to all of you. So that will be part of your second exam. But the idea is that you're gonna have the constraint, at least for the supply, you're gonna have the constraint for each plant. And you know that your capacity is limited, so it's gonna be less than or equal to that capacity. So let me write that in here. It is x11 plus x12 plus x13 plus x14 less than or equal to 35, x21 plus x22 plus x23 plus x24 less than or equal to 50, x31 plus x32 plus x33 34 less than or equal to 40. So this is plant 1, 2, and 3. Okay. And for the demand then, it's just the, if you look at the tableau, you're basically going this direction, like x11, x12, x13, x14, less than 35. Same here, same here. Those are the three constraints. Now, if you are going to look at the demand, then instead of going in this direction, you're going this direction. So, you're going to have a supply from plant 1, supply from plant 2, supply from plant 3 to city 1. So, you're going to have x11. So that means that plant 1 is going to supply city 1. Then x21, plant 2 is going to supply city 1 plus x31. Same for this is city 1. Then 1, 2 plus x22 plus x32, x13 plus x23 plus x33, x14 plus x24 plus x34. So this is city 1, city 2, city 3, and city 4. Okay, so there's something missing here. So this is 45, this is 20, this is 30, and this is 30. What do you think about the sign of those constraints? And what sign are you going to use here? And why?
Well, you need more than that.
Yes. So that means that that constraint cannot be less than, because if you put less than, that means that you can satisfy that constraint by supplying less than what is required. But if you put a greater or equal constraint, you know that the minimum that you're going to be supplying is the requirement. If you go over that, that's okay, but you want to supply at least what is required by the customer. So this will be greater or equal. And that only applies to this particular problem. For other problems, you want to use a equal constraint here, because you want to supply only what is required. Yes?
Is the sum of your supply and the sum of your demand always going to each other?
There, what do you mean by?
Like 45, 20, 30, 30.
Oh yes, that's a good question. This, if you add this, 60, 80, 125, then you have 125. This is because the problem is balanced. So demand is equal to the supply. But that's not always the case. You can have an unbalanced problem, and we're going to discuss what to do when those problems arise. But usually if you have more supply than demand, that's not a problem. But if you have less supply than demand, then you're going to incur an extra cost for not being able to supply that particular demand. Okay, so I'm going backwards. So the last constraint is the time constraint, so you know all your variables needs to be greater or equal to 0. And there, again, here's the formulation, the complete problem formulation. So that's for your reference. So this is what we just did. Okay, let's look at now another problem which is related to the distribution of cars. So MG Auto has 3 plants in Los Angeles, Detroit, and New Orleans, and 2 major distribution centers in Denver and Miami. The quarterly capacities of the 3 plants are 1,000, 1,500, and 1,200 cars. And the demands of the 2 distribution centers are for the same period are this one, 2,300 and 1,400. Here I have 2 pieces of information. This sample is coming from your textbook. So the millage chart and the transportation cost per car between the plants and distribution centers are here. Here you see the millage to go from Los Angeles to Denver, and again from Detroit to Denver, New Orleans to Denver, and from Los Angeles to Miami, and so on. And what we do usually is we put a cost to the distance. So you can see how these distances translate into cost. So if you're going to travel more distance, then you're going to have a larger cost for using that distribution center. So in here, you know that the longest distance is from Los Angeles to Miami, so you will see that there's a large cost when compared to these 2 for that distance. So the larger the distance, the larger the cost. So that's the information we have for the problem. Another way to see these problems is using what we call a network. So you have this nodes, arcs, and another set of nodes. This first group of nodes basically represent the sources. These case are your plants. And this group of nodes are the destination, which are your distribution centers. So you're going to have an arc going from each node to another node, basically meaning that you can move from this plant to this distribution center, from this plant to this distribution center, and so on. And each arc will have a cost, which we call a C, and is basically tied to a decision variable. So we're going to talk more about networks in this course by the end of the semester, but this is just giving you an idea of how you can represent these problems using a network. Okay, so let's work with the formulation really quick. So we're going to use the same concepts we used for the first example. So we're going to use the cost to formulate our objective function. So again, we have a cost representing each 0.1 from supply to demand. So I'm going to use X11, and you can see the numbers here. So that means that you go from Los Angeles to Denver, and you have a cost of 80. Then you have 215 to go from Los Angeles to Miami, and then 100 to go from Detroit to Denver, and then 108 to go from Detroit to Miami, and then 102 to go from New Orleans to Denver, and finally 68 to go from New Orleans to Miami. Okay, so now we need to state our supply constraints and our demand constraints. So same way, we have X11 plus X12 equals 8,000, and this is for Los Angeles. Then we have X21 plus X22 equal 1,500, so this is Detroit. And then we have X31 plus X32 equals 1,200, and this is New Orleans. So these are our supplies. Now we're gonna formulate the constraint for the demand. So we have X11 plus X21 plus X31 equals 2,300, and this is for Denver. And X12 plus X22 plus X32 equal 1,400, and this is Miami. And the non-negativity constraints. So Xij should be greater than 0 for I equal 1, 2, and 3, and J equals 1 and 2. Okay, so for those of you who are interested, again, this is a extra assignment, and I'll give you another point. For exam 2, if you solve the problem with the solver, so you can submit that by tomorrow. I'm gonna make a link in the crack site, and if you submit your solution, you can upload the solution, and I'll give you that point.
It was taught, it was Torah, or was the
Solver, the Excel solver. Yes. Okay. How much time still have? So let me, because I want to use some time to discuss the exam. So the general description of a transportation problem, again, you have set up n supply points from which a good is shipped. Supply point I can supply at most is I units. a set of n demand points which the good is shipped. The demand point J must receive at least DI units of the shipped goods, and each unit produces a supply point I and shipped to demand point J incurs a variable cost, Cij. So every, let me go back here, you're able to get those SI unit, DI units, and cost, Cij. So every transportation problem will have this structure. So you have one decision variable in terms of Xij. You will have a constraint, an objective function in which you are minimizing your cost and you're doing the summation of the cost times the decision variable. And you have some constraint for the supply and some constraint for the demand. That's all you have. So if I ask you to formulate a transportation problem, this is what I'm expecting to see. Your decision variable, Sij, your objective function, and your constraints for the demand and the supply and demand. That's all. Okay? So one more thing, just to go and pass the exams. So here are some of the companies that always are looking for people trained in logistics, transportation model optimization, HEB, Walmart, UPS. So if you click, let me see if I can. Here. No, that's bad. It's taking longer than expected. Okay, for instance, if you look at HEB, they have a transportation division, and they have a couple of opportunities in that particular area. I was searching for same thing for Walmart. You will see that they have a logistic division, UPS, and so on. So again, as I mentioned earlier, you see those tools help you find a job in these companies that basically do mostly logistics and product shipment and so on. Okay, so I'll stop here. And now I'm gonna pass the exams. Again, I was